I'm Uri Goren from Yahoo. I'm a research engineer over there. And today I'm going to share a very simple but practical advice when it comes to averaging. So this talk will be an intro to Bayesian analysis applied to churn analysis. So let's start with the definition. The first notion that we're going to introduce is dwell time. Dwell time is basically the amount of time a user spends on our property before he or she decides to churn. So the example that we are going to follow throughout this presentation is the amount of time a user spends on our website before hitting the back button. Other applications are how effective are promotion codes. I give a promotion code to a customer. How long is it going to stay my customer? Okay, so our problem settings is as such. All we have is a list of websites, and for each website, a list of all the users who visited it and the amount of time they stayed. We don't have any data about the websites other than its address. We don't know if it's a gaming website, a news, or whatever. We don't know nothing about the users, so we can't do any better matching. So basically, the data is as simple as that. An array of websites with a list of dwell times. And given this data, we are required to predict how long will a new user visiting, for example, site 3, how long will stay in our website. So given this kind of poor data, there isn't a lot of things we can do. I think that the straightforward approach that everyone is going to take is basically average the dwell times of other users who visited the same site. Just a moment about the notations. So DI is the dwell time of user I in our website, for example, website S. And ES is basically our best prediction, which is the expectancy. How long do we expect the user to stay? Now, I think we can all agree that this is a good prediction when n is large. We also have a very nice theorem, the central limit theorem, that guarantees that it's going to be as accurate as possible as n grows. However, what do we do when n is small? So this is a crucial point at our analysis, and we need to introduce a bias. So this is basically two ways you can go. Either you're going to say, if I have less than 30 observations, I have nothing to do and give up. Or you try to introduce some prior knowledge. So here we introduce prior knowledge in the form of pretend visitors. For example, B is our bias. We can try and calculate the overall dwell time across all other websites or any other bias that we want. And M is the mass of the bias. For example, I imagine that we saw M users who stayed on the website for B time. So with this assumption, I can apply the previous solution without any problem. Just average them out. So you might have not noticed, but this is a Bayesian model. We actually introduced assumptions. We introduced prior knowledge. And with this assumption, we actually went to the Bayesian side. And what are the assumptions that we made? I'm not going to prove it formally because we have only 10 minutes, and also I don't think that important. Basically, we assumed that the distribution of dwell times is a Gaussian. If you want some intuitions as to why is that, you can assume that basically the overall assumption is going to look around B, around our bias. And basically it's going to be as wide as our mass is. So why assume a Gaussian? Actually, everyone who dealt with churn analysis knows that actually the more time pass, less and less user do we have that stayed, more user churn. So this is a classical churn rate decay. And it looks kind of an exponential decay from where I'm viewing. So let's try and model it as an exponential decay. So this is the exponential distribution. We have a parameter lambda. And what we try to fit is the best lambda that would fit our data. So with Python, there's a very nice library that I'm not going to talk that much on because Shlomo is going to have a full talk on PyMC. But this is kind of a teaser. So with 3 lines of Python, what we have here is a model that numerically analyzes, given my assumption of a dwell time which is exponential, and I assume that lambda that we saw before is Gaussian distributed around our bias and our mass. This is where I'm going to cheat and kind of rush over the details. Why should I assume that lambda is distributed as a normal distribution? If I'm going to assume that it is distributed as a gamma distribution, then basically all the math work out and we're going to have a beautiful formula at the end of this presentation. So if the formulas work out, basically, this is not a formal definition by no means, then we call the distribution a conjugate prior. Okay, so given gamma that have 2 parameters, alpha and beta, I choose alpha and beta that have the mean that I want, for example, a fourth. Again, rushing through the formulas, I'm cheating a bit. And at the end, I know that the distribution, given the assumption of the exponential likelihood and gamma posterior, is going to look like that, which means the initial alpha and the amount of dwell times that I have, and the denominator, beta, and sum of 1 over the dwell times. If I rephrase the parameters as alpha is now called m, and beta is now called m divided by b, whoa, I get this formula. Maybe this rings a bell for those of you who have some experience in physics. This is called the harmonic mean. The harmonic mean basically pops its head when averaging speeds or decay rates. For example, if I traveled here half the way in 100 miles per hour and the other half in 50 miles per hour, my average speed is not 75 miles per hour, it's actually 66.
What is half of the way distance-wise?
Half of the way distance-wise. Okay, so this is what I expect most of you to take from these lectures. Is not the gamma distribution and exponential function and what have you. It's just when you analyze data, first try to plot it. If it looks centralized, then basically the straightforward mean should be good enough for you. But if it looks like an exponential decay, maybe the harmonic mean is a better fit. So